Yeah, so I will be talking how robotics helps me understand what is language. So what is language? Well, in some ways, you have some kind of brain activity on the left, in one person, and you have another person on the right, and then you have an interface, which is like this red dots. It's a sequence. It's one-dimensional, and it's discrete. That's what language is. It's a short, one-dimensional, discrete sequence. That's all it is, nothing less, nothing more. And by having, and this sequence, only this sequence is shared between both brains. And somehow, by having these sequences, the left side will modify something on the right side. We don't know what. So it's pretty, this is a pretty major thing. I think in the history of the universe, this happens only twice. One is the DNA, right? You have a finite, you have a sequence which is one-dimensional and discrete, which transmits information, complex information. We don't know really completely how it transmits it. And language is the second time. And this is, so this is really fundamental. That's my view of language. It's not completely standard, but I mean, it's pretty, and as you can see, there is a lot, I added a lot of little pieces of optimization robotics there. I mean, assuming that part of the brain is actually solving already a lot of the problems you are solving, but hundreds of thousands and thousands of those. The interesting thing is when this happens, so this took like between 2 million years and 300,000 years to evolve. You have to start from one point. The key differentiator is going, one point is actually a discrete element. So it's like a sound, a unique sound. And in languages, you have between 20 or maybe 1,000 different sounds. And the key is to have two. Once you have two, you can have three. So the evolution is probably going to 1 to 2 to 3 to a sequence, which is about a sentence here. Once you have that, the fact that you communicate reflects back into your own brain. So you create more structure as you use that element. In particular, you create discrete symbolic things, which I put these predicates here, some kind of logic. And you also have, once this happens, language bounces back in your brain. So that's why when you think, when you think about thinking, you think it's only language. It's because language is everywhere, but it's not because it's everywhere, but it's not everything. So so now you have that, and how do you try to describe the connection between the models on the left, the models on the right, and this interface here? It's what you have on the left is extremely complex. It's your entire brain activity, your entire experience, and it's mapped into that single sequence. So that's my interest here, is that in order to describe the middle part, we need to understand a little bit how to connect it with some optimization that you have on both sides. So natural language processing, which questions did it try to answer? So I break scientific questions into two parts. So maybe we say, okay, natural language is a mapping between what you see, the sounds or the words written, and something. And the question is, okay, what is that something that you map into? And then how do you do that mapping? Is there an algorithm that you can describe that does it? And then the secondary question, which is a bit simplified, is okay, maybe if you cannot describe the mapping, maybe you can just have a model that describes what is the correct sentence and what is not the correct sentence. And then from an engineering standpoint, NLP tries to answer that question. Where is it useful, basically? And so going back in the 50s, late 50s, 60s, you had these rewriting rules, and you say, okay, maybe we can describe what is, so you have a sentence here, why is it correct and why is it not correct? There is no book that you can look up systematically and figure out where it is correct or not. And it's even a sentence that's like copy and pasted that from a New York Times article, its first sentence, it's extremely complex to figure out why it's correct or not. And people say, okay, let's have this formal, maybe context-free grammars or more elaborate grammars. It doesn't matter what's the formalism here. and that describes what is correct. And when you do that, you actually immediately map it into something. So what you actually define is a mapping. And people say, okay, we were just trying to answer the question, what is possible? But we actually defined a mapping. So is it a mapping into something that's real, or is it just a trace of what you are trying to do? And so this started in the 60s, and there was I think a failure of natural language processing, not because the method didn't work, but because people didn't acknowledge it didn't work. So they tried. People say, okay, we have this formalism. Where is the book that takes this formalism and describes the English language? Where can you find it in your library? Is it a book like that? Is it a 20-volume encyclopedia? Is it the entire library? Where is it? No answer, and nobody actually talked about it. So this failed, which is not a problem, and that's the way science works. But people didn't acknowledge it was failing, which is a problem. And then you had a question that were really never answered. What is the scale of that? I mean, is it 1,000 rules? Is it 1,000,000 rules, 1,000,000,000 rules, 1,000,000,000,000 rules? I mean, there was no answer to that. And this looks like a formal grammar, but it has nothing to do with a compiler of a computational programming language. Programming language, you can define it in like 500 rules, and you can parse it in linear time. Here it's bigger, and every basically a serious parsing algorithm was in exponential time. So what happened is that people actually, it became too complex and they got rid of the complexity. So they cut it down to things like, okay, let's remove the trees. Let's try to make some dependencies. Let's try to do simply to find the power of speech. And people, because they couldn't make a system that was working, they found a way to actually get funding. It was to actually define measuring system that they could improve upon. So even though it was not really actionable, that was the way to move the system forward. And then I think the complexity went down and down into for 40 years, basically. And there was some parallel work in linguistics to try to say, okay, let's move back and let's just try to describe what's happening in the language to figure out the scale and what we can do with that. So basically, what happened is that the first part was dropped. People decided, well, we cannot just answer that question. And it was the problem also is that it was not really acknowledged that natural language processing stopped somehow to be about science. It was saying it's too difficult. There was a part of linguistics still working on trying to analyze things, but linguistics became purely an engineering question. Where can it become useful? So, and then you had deep learning coming up in the late 2000, like 2008, 9, etc. And suddenly you had massive improvement in the first two applications were machine translation and speech recognition. And suddenly you had things were improving very slowly and then dramatically they improved. And actually they improved so much that the tool became useful. I mean, you use Google Translate and translation everywhere. Speech recognition is everywhere. Speech recognition is pretty close to what a human can do. And machine translation is pretty good quality, even for languages that are pretty far away. And in 2018, you had this talk from Jeffrey Hinton at the Turing Award in 2008. And he said, okay, you can see here he tries to separate logic-inspired approach, which is the symbolic analysis of languages, with a biologically inspired approach, which is what he's doing, deep learning. And during his talk, he says, okay, this is basically deep learning 1 and symbolic AI lost. So he said, is this a final nail in the coffin of symbolic AI? And during his speech, he says, yeah, it's symbolic is as lost and there is only deep learning. And okay, so now if you look at that problem a little bit, so you have Google Translate here, so it's pretty nice. But if I give you the translation, I mean, it's probably good, but do you know whether it's good or not? It's actually a little bit ambiguous translation. And imagine that you have this. Let me take this image. Imagine that you have a surgeon, an AI surgeon, who is better on average than any surgeon. The only problem, so if you go to the hospital, you get that AI surgeon, he says, this is the best guy, nobody beats him in average. There is only one problem. There are a few surgeries he doesn't know how to do. It's fine, that's fine, every surgeon cannot do everything. The only problem, he doesn't know which one he doesn't know, right? So you are going there and you say, okay, this is it, so I know Google Translate is very good on average, but is it good here or not? I don't know. It doesn't know. I mean, it has internal numbers that will take how confident it is about it, but they don't really mean anything. It's not going to be able to say, I don't know. Whereas a translator, even if it's somebody who is not really trained, they will immediately be able to tell you, I don't know how to translate that, which has huge value compared to that. So how do you go about that, and why is it? Is it really fundamental to what deep learning is doing, at least in natural language processing at the point where it is now? So you can think about deep learning in natural language processing as propagating uncertainty, right? You start with a sequence of words, word embeddings. It's a big vectors of numbers, I mean probability numbers, and then you map it, and at the end you get the translation, you get symbols. Or you can think of deep learning in terms of image recognition, dog versus cat. You get a massive amount, you propagate the numbers, and at the end you get two labels, dog and cat. So it becomes, everything is float, everything is continuous, everything is unknown until the very end when it becomes the answer. So, but this is what the problem is for translation. If you propagate uncertainty and you provide only the result at the end, then you don't know why why you are producing this result, and you cannot say whether the human can use it or not. So the question we are trying to answer is, rather than propagating uncertainty, can you propagate certainty? So we put this family of algorithms together, which is a way to look at parsing. Maybe we start, what we like to do is look at language really from I like this word from Franz de Waal that says science is, you have to start with respectful observation of things. So you have to spend time looking at what you are studying, and you have to spend time looking at the sentences and analyzing them and trying to understand what's happening, which is something which deep learning doesn't do. I mean, it's a different approach. It's so here is the outline of the algorithms. We represent sentences by these spaces, which is very simple. It's just a set of rectangles. You can think of them as words or word groups, etc. And they have a label and they have a span. That's it. So you have a space on the top. It's some kind of representation of a sentence, and then you want to transform it into a space in the bottom. And here, I don't know if you can see. You just this is an expression that expresses this transformation, and it removes this label here, which is gone below here, and it adds this based on some geometrical constraints of the rectangle. And the constraints, so what we do is look how the rectangles are next to each other. So two rectangles can be one after another, they can touch each other, or they can be parallel here, or they can be embedded in one, or aligned on left and left, right, etc. And just so you have these operators here that describes the position of two rectangles compared to each other. And with these operators, so which are used here, and this to just remove and add, you can transform all this into finite state machines. So here, finite transducer or two transducers, which is actually B machine. So you can actually have potentially millions of these things and apply a transducer to your input sentence, and you apply it repetitively. So this looks a little bit like that. So she's reading a big book, and you got it starts by the thing on top. You get to dictionary lookup, so that's how it starts, and then gradually you recognize, okay, you have something reading before an article here after a pronoun, and maybe you can add this kind of thing. So if for those of you who are familiar with grammars, it can be contextual, and very important, it's not a tree. So this is not a tree because you can go back into any analysis that you had before. So this is, you would have all the rules. So it's the same rules that are applied repetitively on the same element. So, and you can think about the rules as a global grammar, a global model of a language. So this goes from this to this element, and then this element, and then here you can see that basically you have disambiguated your input sentence. You can modify this algorithm a little bit to make it do what I call like propagation of certainty. And I will show you it's a nearly deterministic parsing, which is completely different than what traditional parsing algorithms, which tend to be exponential. But this is deterministic with in quote because it's as the person talks, they will make it deterministic for you, knowing what you know about the domain. So that's something which is a little bit more complex. So here is an example in which the gray part is things that are unambiguous, the white parts which are still unknown, and you can see as you move from top the input to the bottom, things become more and more gray, and basically they become everything which is gray is certain. So you move down this path, and the idea is that at any point there is always something that you can do for sure, but you never know where it's going to be. And basically the person, the model, the idea behind that is the person who is talking is building this so that this path will exist. So it's very different from traditional parsing in the sense that it's not from left to right, it can be anywhere. And the person, if I know, you know what I'm talking about, I don't need to make it as long. If I'm speaking now, like now, I need to make the sentence much longer in order to generate that path. So at the end, what is the model of a language? Here it's a sequence, it's a set of transformations that are combined to one single thing. So one finite state machine, and this thing is applied to every sentence repetitively until you reach a fixed point, until nothing happens to the input sentence. So now the interesting thing is now we have built a machine learning problem. And it's realistic in the sense here you have a set of sentences that are already analyzed. And we call them like movies. It's just a sequence of frames, right? A sequence of. So this is the movie here for one sentence. And if you have a set of training data, can you actually generate these things? And what we hope, so we haven't proven that, but is that the training that you get is completely different from what's happening in deep learning. So if you get like GPT-3 or like 2020, it's not the biggest, but it's already has 175 billion parameters. It's trained on 500 billion tokens. So this is big. So now if you analyze linguistically, what can you expect? How big does this need to be to create these things? I mean, we by linguistic analysis, we think it's going to be around 500,000 tokens, which is 1 million times smaller. So the goal is to actually create a machine learning that will build a model of a language, which is not, people are trying to make models now, but they are trying to make it 20% smaller, 50% smaller. We want to make it 1 million times smaller. And the idea also, if you can make a model that much smaller, you get closer to the reality of what you are describing. And there is a big argument that says like this huge model, they are so huge that it's not clear exactly what they are describing. So, and then you can, from that, you can imagine a model of language in general. What you have is a set of movies. Rather than, you don't actually need to do the machine learning in your head. You just have to have a reference sentence. As you grow up as a child, you accumulate a number of sentences that you know how to analyze. You also have the ability, that's something which is very specific, I mean, for humans, but we share with animals, we share with birds. We can memorize sound patterns, a lot of them, at least 100,000 of them. So these patterns are kind of a memory board that holds all these movies. So you can hold in your mind 100,000 sentences like that. So it's a plausible the idea of a representation of what language is. So I just want to mention something pretty important here. So this simple thing here, no human-specific capabilities. There is nothing in the brain that a unique feature in the brain that makes this possible. It's just the general feature of the brain that we share with many animals that are just expanded that allow us to do that. And it's been a question of philosophy in the past century, at least. And that's one of the big divergences with Chomsky, for instance, who says there is something specific, like a specific location in the brain that can do languages. And this says, no, you don't need that actually. And it's not proven because we need to actually run the test and build the language, but it's a path towards probability. So it's actually the model. If this was pure syntax, and syntax is not completely enough, it turns out. And I go back to the original module here, NLP just being a module. And the traditional view of NLP is you parse, and then you map the parsing into something, representation logic. And it's been a question, at least for 2 millennia. What is logic? And everything always starts with the study of language. You could go back to Aristotle, or more recently, George Boole, all the Gottlob Frege, every single advance in logic is based on the study in language. And the big question is, okay, what logic? Is it predicate logic, first order logic, second model, etc.? And so there are two things I want to say there. Is that so it's wrong in two ways. So first, you cannot break it down. You cannot break syntax from semantic. It's really put together. It's more an anatomy kind of thing. It's mixed together. And also, the other thing is that there is no single logic. So that's, I think, one of the problems that language had for a long time. People were trying to find the logic that can represent a language. And when you go from first order logic to predicate logic, first order logic, etc., modal logic, everything is driven by language with the hypothesis that there is only one logic. And the answer is, I mean, it's all logic. We're actually using all possible logics at the same time into small universes that are connected to each other. And this is, I'm trying to represent it that way, is you have, when you think, you actually think partially in some logic, partially in other logics. And so here I just put predicate logic, modal logic, but there are other things there. And the key thing, the reason why it works is that these things are connected. So they are not completely independent. You may think at the same time in two different logics, and you have some mapping between some elements in different words that you are trying to think about. And this is where robotics become interesting, is that it's not only logic, discrete things, it's also models that are continuous. We think through logic and through the continuous world. And the challenge, what we are trying to do, is actually re-inject that into the syntactic rule so that we make it completely deterministic. So this is, I just want to mention a lot of work from Gilles Fauconnier, who spent decades trying to describe how different logics can be actually linked together. Just one final word. Metaphors and heuristics. So metaphors are generally thought as a secondary thing of language, and heuristic is thought as a secondary thing of logic, right? It's just techniques to help think better. Actually, the point here is they are actually not peripheral, they are central, and they are actually the same thing. Metaphors are heuristics. Metaphor are defining the link between different logical words. between logical words and the continuous words is defined in the language. If you say, so here is an example, right? So if you have a type example and you want to log in, just these simple sentences, how long can I stay logged in before you kick me out, right? So what is kicking me out have to do with logging, being accessing to a computer. There is no notion of space, but because you use space, you actually use all the reasoning that you are capable of doing with space on the fact that you log in. The entire syntax of space, the entire modeling of continuous, what it means to go in and out, is in that sentence. And if you can reinject the fact that logging in is actually connected, you can put mappings between the logic of logging in and the logic of moving in and outside, then that's what you have. That's what the metaphor is. And the heuristic is, if you have a mapping between people try to do semantic, that would be huge. Tim Berners-Lee wanted to build a semantic web, basically billions of facts about the universe, and you could actually think about it. And Prolog is a programming language that tried to do that in the 90s also. And the problem is you could describe the entire logic, but you could never find a way. It was always too complex, exponential. And what is happening here is you can actually use these metaphors to do shortcuts and to find your way out, basically. So this is an example of like from the 90s about how it affects things. If you look at that's description of sentences in the Wall Street Journal about the stock market, and it's metaphor everywhere. And if you want to analyze that, you need to connect like objects going up physically. What does it mean to go when we talk about an object going up physically, and with the fact that some average is going up or down. And that's something with metaphors, is they are in every single sentence. You cannot talk without metaphor. You can actually not think about metaphor. And you cannot think actually ontologically. You cannot walk from this table to the door just by logic. So back to I finish here. So what I'm trying to do is really have a model. So it's not going to be the entire, it's impossible. I mean, the entire human cognition is too big, but the goal is to have some elements, and you can show that you can link with a model of language, and then you can actually build an algorithm and a machine learning algorithm that you can, that will generate a model of language that you can actually apply to a translation and then produce potentially. I mean, we haven't done it, but that's the direction in which we are going, in which you can say, here I know what I'm saying, and here I don't. And I'll stop here. Thank you.
Thanks so much, Dr. Roche.
Thank you, Dr. Roche, for your presentation. So I was wondering, bringing back the debate between deep learning and I would call it a more disciplined approach to natural language processing. I cannot help but think what people are talking about now with dynamical systems, which is something like physics-informed learning. And so I was wondering if there could be like a something that would be of the kind grammar-informed natural language processing via deep learning.
Yeah, so I think that the lesson, and that may be a challenge for you, is that can you have multiple models that may be completely independent of the same physical reality that you would link together? So you would think separately, and possibly not only two models, but maybe hundreds of those. And some of those could be formal, could be logic. Some of them might be completely, I mean, the kind of things that you probably usually do, which is continuous computation. But some things may also be logic. And if you can link them together, then maybe you have a solution which is more robust than any individual part.
Thank you.
Hello. Just a quick question. We come from a business background, so our questions might not be as deep as the other questions. But sometimes in natural language processing, it's harder to work with some languages than, for example, it's harder to work with Arabic than English, right? And I just wanted to know why, from a technical perspective.
And if you do deep learning and translation, it's mostly about data, how much data you have. So English has by far the largest amount of data available. So that would be the difficulty. Otherwise, there is no real intrinsic problem for any language in particular, as long as you have writing for it. Right? That's I mean, for languages or dialects that don't have writing, that's a different challenge. If you have writing and you have data, there is no difference between languages in terms of difficulty.
Okay, so if we have enough data, we can create machines that can realize the Arabic language just as much as English.
There is no reason why it doesn't work in the same way as in other languages.
Okay, thank you.
Thank you.